everyone. Thank you all for coming. It's my pleasure to introduce you our tonight's speaker, Dr. Giulia D'Angelo, who is a researcher at Faculty of Electrical Engineering at CEU in Prague. She is a Marie Curie Sklodowska Fellow and recipient of International La Technovisionnaire 2025 Award. And tonight she will tell us something about selective attention and neuromorphic algorithms. Thank you and good one.
Thank you so much. Okay, I seem important, but I'm not that important. I have one mini update. I'm not a Marie Curie fellow anymore. I'm an assistant professor at the Czech Technical University in Prague now. So this is my past. So this is where I come from. I did my master and bachelor from the University of Genova, then King's College of London, Manchester and IIT, and this is my future. So the guys that you see here, those will be actually the guys that will work. And now I just need to write grants. So can you smile? Can you? It's going to be long. It's going to be painful. So let's do it together, okay? Because it's not going to be easy. Okay, so I will talk with you about event-driven sensing and neuromorphic computing algorithms and computation for active vision. Let's start from the very beginning, okay? It's going to be long. I'm saying it. Now, who of you have seen my? We know that I know that. What is the guy that? Yeah, you saw it already. There's anyone else that saw my? Oh, ciao. Saw my presentations already? No, new. Fine. Let's go with the flow. Okay, this is our dream. Please come in. Hi. So this is what our dream, right? What is it? It's me taking a meeting, a very boring meeting, whilst my robot is giving me a cup of tea whilst it's cleaning, right? So this is where media are making fun of us, thinking that this is already happening. It's not, right? It's not happening. Otherwise, where is my robot? So yes, this is what we would like to happen. And what we actually want is for the robots to move in an unconstrained environment. So we have an environment that the robot never have seen. Ooh, don't tell the deep neural network about that. And we want low power consumption and low latency. Low power consumption means 1 watt, no more than that, okay? So a normal Jetson Nano can get to 10 watts, which is incredibly low, but a normal GPU can get even up to 100, 150 watts, which is unbearable if you need to do lots of skills, right? If you need to listen, walk, and do lots of things at the same time. Oh, hi. Then what we want is also low latency, okay? So if you talk to a robot, and then the robot is like, you ask for a question, then the robot, that's not human-like, right? We get very bored immediately. So the latency is actually one of the most important things, okay? Let's go on. Okay, now, do we have robots that do such a very easy thing for the cat and for the dog? So you have the cat there that is just playing around. Do we have a robot like this? Guys, it's not going to be just me. You talk tonight, okay? So do we have a robot like this? Oh, thank you. And we don't have it. No, we don't have it because it's very, very difficult to make a robot do something like this, interact with something in a very easy way in this with a toy or whatever. Like it's the same for the dog, right? It's very difficult to train a model to do everything. Understand that it's getting the food when it is giving the paw. That's fine. But how do you do that? Plus balancing, plus hearing, plus doing lots of other things. Okay, for now, we have a vacuum cleaner that we usually follow for the cables, right? That's the most robotics that we have. Okay, let's look at this guy, okay? So this is just, I mean, I don't have kids. At some point I should. But anyway, this is possibly 1 year old and is interacting very nicely with a toy, right? So now, in this very moment, I'm looking at you, I'm like, oh my God, it's like 1 hour talk, will I get to the end of it? And then I'm thinking, okay, I need to walk because otherwise I will be boring. And all of this, it's done with 20 watts, okay? Our brain does everything we do with about 20 watts, okay? So now let's go back and think about those GPUs and those deep neural network scientists that get out with one single task of object recognition. Yes, that's a cat, in 200 watts. Okay? So how cool is our brain? Fine. Okay, now let's think about the scenario that we had before. Okay? There's something that is going on here, which means my cat is burning to hell, right? Now, question, how do I tell the robot, look, forget about a cup of tea, forget about the cleaning, the cat, you know? That's the most important thing right now. So how do we define attention? What is attention? Intuitively, easy. Describe it, right? Okay, let's go here. Now, I will play a video twice. I mute myself, and then I will ask you questions. Now, who has already seen this video? It's banned to respond, okay? I will, you know, sue you forever. Now, who has not seen this video? What have you seen? No, shut up. What have you seen? So, give it to me better. Explain. Okay. Yeah, good. Something else? Guys, for the love of God. Something else? It got interrupted. Okay. Fine. These are two complete different people. Okay? Nice. What this is telling us, that our brain is making up lots of shit, okay? Right? Is making up lots of things. And what we get out of it is that we just focus on the informative information of the scene, okay? What was important, he was typing on a keyboard, the phone rang, and he responded to the phone. That's it. That's the amount of the information that the brain can cope with. And still we survive, kinda, okay? Fine, let's go on. Now, let's look, so what is this? How do I work with this pointer? Here. Okay, what is this? Ideas? No, you shut up again. Ideas. Bravo, yes. It's a night tracking. It's a night tracking from 1960, okay? So there is another nice scientist, Yarbus, which, I mean, this is really an Italian pronunciation, but he worked on attention, visual attention. So what you see there is on one side, you have, no, you come here. No. Yeah, you stand up and you come here. Come closer, my God, there's 20 people. So here you have on the left the images that the people were looking at. And on the right, you have the recording of the eyes movement. Okay? So let's look at this. What's going on here? So these are the eye recordings, and this is the scene. Why? Yeah, because it's very old, yeah. No, you don't give a damn about the details. You're trying to...
I find that we were looking at this one because of like danger, because we don't know what's in the picture, but it took our attention because in some point of view it could be dangerous.
So this is true in another of the picture. What she said is everything right until the detail. We don't care that much about the details. What do you do when you hear someone screaming outside? I don't know, maybe this is too much of an Italian thing, but what do you do when you hear someone screaming outside? The first thing that you do is like, oh my God, what is happening, right? You go there and you look at it. So what you're trying to understand here is, are they fighting? Are they discussing? What's the matter? You know, you're trying to know the situation, right? So you meant with the details what's happening among them. Okay, yes, definitely, yes. Then here, the other thing that is happening here, you know, guys, right, is triangulation. Easy. What is happening here is what you were saying, right? So foliage, bear. Okay, and then I need to run. Now, after all of these studies that Jarbus has done, at the end of the day, what he came out with was like, look, do I understand attention? No. I can tell you that what we look at is the most informative information. What this means is still yet to be understood. Okay, now we have an image, we have a scan path that now we know is the recording of the eyes moving. And then we have a saliency map. The saliency map is basically the concretization of our fixations, right? So where we fixated the most. Okay, so 1998, E.T. Loren, Christoph Koch, and Ernest Niebuhr in 1998 came out with this first model of attention, and this is basically extracting the feature. So here you can see that he's extracting colors, intensity, and orientation. Okay, so he's extracting the features of the visual scene, and then somehow getting some sort of pyramid, so scales, different resolutions. So to be scale invariant, and what you're doing is trying to get at the end a winner take all, and what a winner take all means is just selecting the maximum point of this feature that you extracted. Well, cool, but feature extraction is not enough. Why is not enough? Because think about it for a second. How do we understand that this is a thingy, right? It's a thingy on its own, right? Like all of it, it's a plant. You might say recognition. Well, it's not that easy. It's way more complex than this. Yeah, give it to me. Bravo, yes. So what we do is that we get the bottom up, you know, the stimulus-driven things, and we try to make sense of it, okay? So the first thing is trying to make sense of edges and see if those edges can be an object, and then you go to the recognition. Yeah, exactly. Okay, fine. Gestalt principles. In 1950, and you have a nice reference. I mean, I take a lot of care for my slides, honestly. So in 1950, you have Gestaltism, and if there is a German here, would say that Gestalt means whole or integrity or entire thingy, okay? And this is actually, there are two schools of thoughts here. You have the Gestalt that is basically telling you, look, we understand that this is an entire thing, okay? And then there is a Treisman and Gelade that says, no, we have, like I get all of the edges and then I combine all of the edges together to understand that this might be a bottle, okay? So in one case, we get a blob, that here there might be something interesting. In the other case, you get all of the edges and then you combine the edges and the combination of the edges create the bottles, okay? Now, what you get here, yeah.
One German is here.
Can you tell me exactly the I know that it's like the whole, but... Yeah. He's German for real. Like, of course, yeah. Yeah, okay. Yeah, go on. Thank you. So the way, yeah, I don't know exactly the terminology of that word, but Gestalt, I don't know how to say it. Okay. Okay. The way it's described from this movement is that you perceive an entirety of the thing. So it's not split in pieces, it's an entire thing. Yeah. So basically here, in this movement, you have perceptual rules to understand vision, okay? So these are the rules that these psychologists, because this is actually philosophers and psychologists, that they think that we use these rules to make sense of what we see, okay? So here we have the closure, right? So what's here? What is this? Fuck you. What is this? What is this? And this. Bravo. Nice. Lots of biscuits later. But point being, you take it for granted. But it's not that easy. It's cells that are actually telling you, oh yes, say square. It's cells communicating with each other. It's not that easy, right? Same thing here, similarity, okay? If I ask you to group these things, you would group circle by circle and triangles with triangles, right? Of course. Same thing here for proximity, same thing, and this is figure ground organization. So you understand that I am here and the blackboard is here, okay? So the distinguishing between foreground and background. Okay, let's go on because, I mean, it's going to be long. Now, 2000, look at this. This is, I think, I still need to understand, but I think this is Justin Timberlake or something. But anyway, so this is, let's take a closer look on the closure, okay? So these are real cells, guys, okay? These are real cells in the secondary visual cortex. And here what you see is this little black thingy is the cell, and then you have the object that is on the left and the object that is on the right. And the black and the background is of different colors, okay? Now, here in A and C, it's different, the response from the neurons from B and D. So here you have the response of the neurons in time, okay? Anyone has a response for what is different? Can we also close the... grazie. Why is it different? Here the neurons are firing a lot. You see? How come? How come that neurons know that the object is on the left? That's a single cell. It's not easy, right? Let's look here. Let's put the same problem here, okay? We have the same problem of corners facing towards each other, and you that at some point, like at the start of you saying it's a square, there is this cell, okay? Maybe the cell has this shape. Maybe, right? And maybe, as it happens often in the cortex, we have different orientations of the cell looking at the same point. Then you do understand that that is an object. And you do understand that that border belongs to the object. And what a crazy creativity, these are border ownership cells. Okay? Let's go on. This is a proto-object. So it's an object to be. I did not recognize it, but I see that there might be something that is interesting to look at. Okay? So it's a step before recognition. And this can be achieved with this filter, which is the von Mises filter. And with this, guys, we got to the start of my PhD. So this is the von Mises filter, and this is the model that I was using. Doesn't, ring a bell? This is the same model we were talking about before. What's actually happening here is that we have two layers more here. Border ownership pyramid and grouping pyramid. Okay? So here you have the von Mises filter here at the border ownership pyramid. You convolve it with different orientations, and then you take the convolution of different orientation and poof, you sum it up. Okay? And this is how you get the grouping. Fine. There we go. So I jump in IIT, which is the land of ICAB, and they show me ICAB, this creepy guy, and they show me this model. How many of you knows ICAB? We have one in Matei's lab. We have another ICAB in Matei's lab, which is 200,000 euros of very complex, not working robot. It's a bit creepy, by the way, but it has this young face because it doesn't want to scare you out, like whatever. Anyway, so it's very complex, guys, okay? It doesn't work for a reason because it's too complex and it's very difficult to make it run. So as you can see here, for example, we have a hand that has also these two fingers, which are useless for grasping. For grasping, this is what it needs, okay? Just 3. But we wanted the other 2, and then you can have a look to the IIT website. We won lots of awards for the Hannes hand, which is a prosthetic end, okay? Because we are so used to deal with this complex problem of the hand that then the prosthesis went very well afterwards. Anyway, so I am there. I am with the creepy guy. How does the robot perceive, okay? Is any of you doing robotics? Yeah, you don't respond, yeah. You do robotics a little bit, yeah, okay. How does a robot perceive? So we have cameras, whatever, give me the name, microphones, I'm too tired, and skin, okay? Yeah, but how do we perceive? What's the difference? Like, how does a robot perceive? Do you know how does the robot check the sensors?
Just bioinformation which they get from the sensor.
Yeah, that's okay. Yes. Let's keep it there. Let's keep it there. So now the question is, okay, let's see later what happens with robots. Let's see how do we perceive, okay? So let's imagine that this is a receptive field, okay? An area where we perceive something, okay? Let's imagine that if I touch it, it becomes yellow, okay? So what happened in time, it's this, right? So this means that it's the receptive field that when I touch it, is communicating to the brain that something happened, right? You're with me? Fine, these are events, or we call them events. But now, the real difference with the robot is that we are event-driven, right? If I touch here, the information is here. If I don't touch it, it shouldn't. You never know. But the robot, it's clock-driven, okay? So what does it mean is that periodically, every 10 milliseconds, the brain is checking for each sensor on the skin, on the hand, on the microphone, is checking everywhere if there is a value that has changed, okay? So imagine how much waste of data we have when we run a robot, okay? Let's go on. So what is this? This is a neuromorphic ICAB, but what does neuromorphic mean? How does a neuromorphic camera work? Have you ever heard of event-based cameras and neuromorphic cameras? Yes, then you shut up. Okay, fine. Let's go here, okay? So this is how a camera works, right? You have your grid of photodiodes and then click, you get a frame, right? So this means that you get the values of each photodiode at the same time, right? You get a frame. And a sequence of frame gives you a video. So the sampling is on time, okay? What if we have a bottle, and if the bottle is static here, we will have plenty of frames of the same bottle, right? Nothing changes. Okay, what is more disturbing is that if I move the bottle very fast in between frames, you don't get it. You don't get it at all, okay? Let's think now how to sample in time, okay? So, sorry, how to sample in the y-axis. So this means if you get your grid of photodiodes, if in this photodiode there is a light information, right? Like there is a value. If this value changes over a certain threshold, increased or decreased, then I output something, okay? So this is exactly what's happening, right? Increased over a threshold, decreased over a threshold, right? Then what happens is that if the bottle is static, I see nothing. If the bottle moves very fast, I catch all of it, right? These are events, okay? And every event has with it X, Y, timestamp. So each event has the time of when happened and the polarity. And these are the event-based cameras or neuromorphic cameras, okay? These cameras are bio-inspired because is exactly what is happening in your retina, okay? I see you kind of like, oh my God. Is it? Anyway, yes, it is. And so what happens here is that given that you don't have frames and what you communicate is dots, and you communicate the dots only when something is changing, this means that you get microseconds latency and milliwatts to few watts power consumption, okay? Let's go on because there is tons of shit to say. Okay, now let's go back to the creepy guy. Creepy guy plus creepy cameras, okay? So this was the start of my PhD, and then I said, okay, I want to make iCub attentive because that was still the goal. I want to make iCub attentive, and then I want, 3 channels of information for iCub. Intensity, depth, because I want at some point to iCub, to do something with the objects, and motion. Motion is inherently interesting, and therefore that was my 3rd channel. So this is what I managed to do at the end of my PhD, part of losing my mental health completely. And these are 3 channels of information, as I was saying before, right? So there is intensity, depth, and motion. As you can see here, there is something known, right? The von Mises filter. So this is the model I was explaining before, right? The attention model I was explaining before. So in one case, we have the intensity that is going through the proto-object model. And in one case, we have the depth, right? So what will be important will be the closest object to the robot. Here, we have something new that I will explain later, okay? And this is motion. Motion doesn't go through the proto-object because if I now throw something at you very fast, you don't really care. Oh, that's a bottle of mineral water. You don't care. You just need to, move away. Fine. Let's go on. Okay. Now, I'm going to go very fast on this, otherwise tomorrow morning we are still here, okay? So you either trust me or you send me an email with your comments and questions. Fine. So this is the model that works with event-based cameras of the proto-object model. The proto-object model is actually the model of visual attention taking inspiration from the cells that we were talking about before, okay? Nice. So this is how it's working. If the video will play. Yeah, there we go. Okay. I have no way to put the video where I want. What do we do? What do we do now? Where is... I need the help because I need to move the video where I want. Whatever. Maybe. There we go. Okay, fine. Sorry, the mouse. So here you have the events. No, let's go back. Here you have the events. And on the right you have the attention. Okay, so you can see that he was interested in the mouse and here in the cap, then in the mouse, and then I distract with a paddle. You see that there is lots of attention here. And it's completely disregarding this line here on the back, okay? Because it's not an object, it's just a line, okay? So let's go very, very fast. This is instead the depth channel. And yeah, this was actually the one that I needed to bring here. Okay. Let's stay here. Now, here you have the RGB video. Here you have the rectified stereo event. Do you know what rectified means? No, thank you. So our eyes have a divergence angle, okay? So what you do when you rectify, you put the planes one next to each other, okay? So these are the rectified stereo events, and then you have the disparity map, okay? The disparity map is very similar to having a depth map, right? So the higher, is just the opposite. It doesn't make sense in grammatical, whatever. So the higher the disparity, the closer the object, okay? So it's the opposite of depth. So there we have the disparity, which is the displacement between the left and right eye, okay? The projected in the left and right eye. Now here we have the proto-object model, the normal one, the intensity channel, and here we have the depth input into the model, okay? Now, if I play it, you can see now there is an object, right? So the point of interest is on one object, okay? Now I'll put another one. And you see that the point of interest is pinpointing between the two, but here is solid on the closest one. So this actually is to solve the problem that if you have the robot, you cannot do, you know? Now this, now that. So now you can tell the robot, look, take the closest one, okay? Are you still alive, guys? It's going to be long, but I promise I'm going to be fast. Indeed, you trust me, I'm a good scientist. Fine, let's trust me. Fine, now here, what happened here is that we have the intensity channel, okay? So we have the intensity channel here, but I wasn't happy. I wasn't happy because I was using the event-driven cameras, but I was still using GPUs, right? Why? How does a neuromorphic platform work? What is it? Let's look at it. Now, in normal computers, we used to think, and we know that we have a CPU, you compute 2 plus 2, you take 4, you put it out on the memory, right? You put 4 here. What if you need to do plus 2? You take this 4, you put it back here, you do plus 2, you take the 6, and you put it here. Is it efficient? Let me drink. I can't finish this thing. It's too long. Is it efficient? Thank you. Okay. Now, what is it efficient? Neurons. Okay? So this is exactly what's going on in neurons, right? So this is a membrane potential. You have the membrane potential that is going up, is a resting phase, and then is depolarizing and repolarizing. How it's happening, it doesn't really matter. This is what is happening, okay? Then what you have here is a threshold. There is a threshold. So what it means is that if the membrane potential, which are the voltage, okay, of the member of the cell, if it goes up over a certain threshold, then you consider that to be a spike. You consider that to be an event. You consider the cell, it's actually trying to say something, okay? That's a spike. And what is this? A train of spikes, okay? So you have lots of spikes from the cell. The cell is trying to communicate something in this way, which is 0, 1, right? It's very easy. Fine. So these are neuromorphic circuits, neuromorphic devices. You have different of them. So this is Spinnaker. Here you have the SPAC. Here you have Loihi from Intel. And here you have Dynapse from Zurich. So what's the difference is that you do not have, you know, to go out and in from the memory. What you're doing here is that you are computing and having the memory in the same spot, right? Because the membrane potential here is increasing over time depending on the input. So you are increasing a little bit depending what happened before, that's memory, and you're computing, right? You are actually increasing. So this is actually the proof of co-location of memory and computing. Okay, so this is neuromorphic computing. This is a mini tiny cell. You can get lots of cells, so you can have a population of neurons, and you can have your spiking neural network. Okay? Now, the difference is that here you have, you know, this is the CPU, this is all of the nice and whatever GPUs. This is the point, right? Okay? 300, 400, 120 watts. And what you get here is milliwatts power consumption. Because what you do here is a structure of populations that communicate spikes. So I'm not giving you a very tough matrix to solve. I'm giving you a spike, okay? Then you need to know how to manage the structure well in order to communicate well your signal, okay? And that's the difficulty of me and now also of Ola and Sharka. Yes. Now, so this is the visual attention model that was from the start running on the GPU, and now is running on this neuromorphic platform. This is Spinnaker. Okay, Spinnaker, it comes from the University of Manchester, where I have done my PhD. And it's actually old but gold. It's never failed me, so I'm very happy about it. And this is the actual model. This is the spiking neural network. So it's end-to-end spiking neural network. Now, look at this. So this is the pipeline on a GPU for the intensity. This is the pipeline on the GPU for the depth. And this is the pipeline on the intensity on Spinnaker. Okay? Look at the latency. It's ridiculous, right? It's going very, very fast. There is a drawback. Sure, yeah, it's not scalable. It's very difficult to scale it, okay? So we need lots of boards because we need gazillion neurons, okay? Fine, but we are working on it. Mazdak, a random Mazdak. so Mazdak is actually one of the guys that I met on Open Neuromorphic, which I'm part of the organization. And he told me, he looked at this work and he was like, oh, I want to use the attention model to do coastline and shoreline detection. And I told him, look, it's not going to work out. But we started collaborating since then, and we changed the model to then do event-driven nearshore and shoreline coastline detection on Spinnaker. So here, what we're trying to do is to catch the shoreline. And what is actually cool, I want to go, let me show you, yeah, what's happening here. There we go. So this is the data set. Here you see the events. Here you see the events monopolarity, doesn't matter. And here there is the coastline from the neuromorphic platform. You see that we catch it, we catch the shoreline. And we wanted to be sure, right? So we tried with fuzzy objects just to see, is it working with fuzzy object? No, we have some spurious response, but no. And then we wanted to augment the data set to see if it was working. Still, it works well. It's just getting when there is the shoreline. Well, the point of this is that I got reviewer 2, which if you don't do papers, you will meet reviewer 2 very soon, if you will. I got reviewer 2 telling me, oh, but why don't you compare with the NeurGB pipeline? And I was like, look, because I give you the coastline detection in 20 milliseconds. A NeurGB camera doesn't even give you a frame in that time, okay? So you might have it with a very good RGB camera, but then you need to deal with the number of data that you have, right? And here, the other important point is that what I use to give you that response with nice accuracy is 0.3 milliwatts, okay? So imagine a drone going through the Antibes, because this is actually the Antibes data set, and it can run for 3 months without being charged, okay? Because, I mean, at the moment we have lots of things that run for 10 minutes, which is ridiculous, and they publish with it, whatever. Anyway, this is not, I don't know why it's not reproduced nicely, but now we are working on a pinball. So what we want to do is to make iCub play pinball very, very fast, okay? Okay, motion. This is the motion channel, still from the PhD, because I'm trying to get a story or to give you a story tonight. This is another model that is running on Spinnaker. Long story short, It's working, you trust me, whatever. The point is that it's giving you the direction of motion, so left to right, top to bottom, bottom to top, in 4 milliseconds, okay? So in 4 milliseconds, I'm telling you, the object is moving from left to right, okay? This, I don't know, I think I'm unbeatable, but you do you. Fine. So this is the end of my PhD, and I'm very proud of you that you got here. And then I asked myself, okay, but wait a second. I understand that there are objects, but can we segment the scene? I tried. I published. That's enough. So yes, this is actually natural communication, so I'm actually okay with it. So the idea is that here, what's different is that you have this recurrent neural network, right? So you go from the border ownership to the grouping and backwards. That basically is like, okay, this might be an object, this might be an object, and you reinforce this idea so much that you end up segmenting, okay? So this is our idea of how our brain segments, okay? These are some results again. There's no time whatsoever. You trust me, blah, 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 blah. Now, after all of these years, right, I was like, okay, nice. Now I have all of the ways to get a saliency map, right? Is there any saliency map in the brain? No. No, there is not. There's actually two schools of thoughts. There's one that is saying, yeah, possibly. And there's one that's saying, no, that doesn't make any sense. So fine. The science, you know, research. So then I started thinking again about my problem, right? And this is the problem that we face. So if you ever done any computer vision lecture, for sure they told you, oh, we look at an image and then this image is inverted in the retina and then pass it through the brain, right? But is that true? No, we move our eyes constantly. It's not true. There's no frames. There's no frame. We are not cameras. Like, you know, it doesn't happen like this. This is what's happening. The cells saying beep, beep, beep. Like, there's no frame. So it's just not true. Okay? It's a very gross approximation of it. You're laughing. It's a very gross approximation of it, because what's actually happening is that we constantly move our eyes around, okay? We constantly move our eyes around, and where we actually see clearly is just the center of your visual field. The periphery is, that's why we make up lots of things. So if you're sure, oh, I'm sure I've seen that thing, wouldn't be that sure anymore from today on, okay? It's like memories. Anyway, since we move around, what I started thinking is, what if instead of object recognition relying on an image to understand that this is a bottle, what if it's us visually exploring the bottle? Okay, so if I visually explore this bottle, the movements that I will do with my eyes will be something like this, right? If I visually explore this, it will be completely different, right? So what if actually learning an object depends on my experience on the object? Okay, if I tell you, this is super easy. If I tell you, put a hand in your bag and take a pen. You have the experience of yourself, you know, looking for the pen, you know how the pen is. What if vision is as much exploratory as all of the other senses? Why is just vision that is not exploratory? Of course it is, okay? It's just disregarded because in all of these years, we have been thinking about the gross approximation of RGB cameras, okay? So what I'm saying here is the movements that I had to do and the region of interest that I could see with, let me play it again, okay? So here you have a region of interest, which is your fovea, where you see clearly, right? And then an action. So you're moving over the object in a specific way. Why it... Now I need this. Yes, yes. What if the sequence, as you can see, the sequence in blue is different from the green one. What if this sequence is actually telling us that the cup is the cup and a book is a book, and we classify it based on our experience? This means that I don't need to see the bottle here with different lighting condition, with different clutter, with different environments, because I do not need to generalize, because it's already generalized because it's based on my experience on it, okay? I hope I convinced you. Sharka is not convinced about the animation. Can we tell Sharka that it's nice? Yes. Anyway, so this is the Marie Curie project that I wrote. And I want to come here as a Marie Curie postdoctoral fellow. And now it's Sharka business. Yeah, come here. So Sharka is a PhD student with me at the Czech Technical University in Prague, and she's working on computational physics, working on SNN for object learning. So it's exactly what I was explaining about before about the perception of the object. Please.
Yes. Okay, so I will start again. Hello, everyone. I'm Sharka, and I'm currently working on this bio-inspired active vision project. And I think Julia almost described it all. But what we want in this project is to have an agent which could learn the objects through active exploration. So we have an agent, let's say in the future it might be the iCup, and it has an object, the bottle, or it could be the banana, and it moves its eyes to observe different points on the object, and it has event-based cameras as eyes. So with each fixation it gets the events, and then it applies the visual attention, so it knows which points are the interesting ones. And what it actually sees is a small region of interest around the most salient point, and then the blurred or downsampled periphery. And this information then leads it towards his next actions. It could be next eye movement or rotation of the object, because it also is able to interact with the object with rotation. And as it continues through the exploration, what we get is actually a sequence of the sensory input and some motor actions, which are coupled together via the sensor-motor contingency. And what we want to build is a working memory which would make sense of this sequence, which would represent it. So we have the concept of the object through learning. And what we do right now is we are building this memory using something called vector symbolic algebra. That's a mathematical tool which represents the information in a hyperdimensional space. And in this space, the objects of same classes will be really close together. And this is how you classify based on similarity. The other option which we want to try out is contrastive learning through time. It does essentially the same thing in a different manner. And to help the agent understand what it hasn't seen through the exploration, we want to try out employing masked autoencoders to sort of fill in the information. And so the final goal is to get an object representation which would be invariant to rotation, or like as invariant as possible. And we would get it from this exploratory behavior.
Yeah, she does the complex math things, and I just say, yeah, that's okay. Okay. Thank you, Sharka. So this is actually the problem that I'm trying to tackle now, right? Like I'm trying to see if we can do object recognition in a different way. And what I actually thought at the start of my Marie Curie is, okay, let's use attention to move to one point to another one, right? But then imagine if you have the event-based cameras and you move them around, and this means that the light of all of the pixels will change, all of the photodiodes will change. So this means that if you move the cameras around, then the full retina will respond Okay, so that's a problem that I had to deal with at the start, and this is what I have done first. So I'm gonna go very, very fast just to show you what's going on. So this is the input from the event-based cameras, right? There is me like this, but can you see or can you tell me what comes from the motion and what is the static scene? It's impossible, right? Because it's just a 0-1, right? It's just events, so it's impossible to say what is moving in the scene, okay? But if you look at amacrine cells that we have in the retina, so in the retina we have more than 200 cells, and if you look at some of the cells that we have in the retina, which are called amacrine cells, they do exactly this job. They try to distinguish coherent and incoherent motion, and this is what I've done here. So now you can see what was actually moving, which was my hand, okay? Now you give it to the visual attention. The visual attention will give you a point, which is the point of most important salient, and then you give it back to the control, and then you tell to the pan and tilt, look, move the pan and tilt in order to put the object in the center of the visual field, okay? Which is exactly what I was saying before, right? We go around because we need to put objects into the central part of the visual field, otherwise we don't see it clearly, right? Like if you look at me and Sharka raised her hands, yeah, exactly. Look at me, you will see her, but not entirely, okay? You see that something is moving, but not entirely. And this is, thank you, Sharka, again. This is the proof that we don't see clearly everywhere in the retina. Okay, and that's the proof why we move our eyes around. So what I'm doing here is I'm saccading. So this is a saccade to put the object of interest in the center. And this is fixation alive movements. Now, we are almost to the end, guys. Like I'm so proud of you. I'm like really, thank you. I will try to make it as less painful as I can. Jurassic Park, okay? You know that there is a nice quote that is saying, don't move. If you don't move, the dinosaur wants... there we go. Yeah, that's my girl. Okay. Yes. So, if we have our eyes completely still, we wouldn't see anything. So why we see? Why do we see? No, no. If you have your eyes still, you see nothing. So you're looking at me right now, right? And you think that you have your eyes fixed. Yeah. You don't. Exactly. You don't. So our eyes are constantly in motion. They jitter. They do this, and they move, and they move, and they move, okay? So we have microsaccades and saccades. Why we have microsaccades? Because dinosaur, if you don't move, okay? So we wouldn't see anything. The information would fade away if we don't microsaccades, okay? Why are you laughing so bad? Is my gestures? No, you tell me later, yeah? Okay, let's go on. Okay, so there we have some nice results from it. I'm not gonna, we don't have time now. You trust me, blah, blah, blah. What I want to show you, we just finished, but ciao. So this is taking inspiration exactly from the amacrine cells, as I was saying before. I'm not gonna spend too much time here, but look at this video, okay? On the left you have the, on the left, you have the events, and on the right, you have the output from the amacrine cells, okay? So there, you can clearly see only what is in motion. So I'm performing microsaccades, so I have the camera here on my leg, and I'm just anxiety shaking, and then I'm saying hello, okay? You can clearly see that just the hand is what you see, okay? And this is how our amacrine cells are working, okay? So far in computer vision, in event-based computer vision, this has been solved only doing ego motion compensation or using the IMU information, okay? So it's actually very cool that there is someone that has done it differently. Me, okay, sure, you know, ooh, sure, yeah, ooh, another benchmark, ooh, okay, good results. Yeah, it doesn't, like, I hate presentations with lots of math and lots of that to scare you. It works. If you want to read more, you just look at my papers and you'll read more, okay? Fine. So, what made me think is that the important actual thing here is the saccades, but most importantly, the fixational eye movements, okay? So this means that if I do not perform well my fixational eye movements, this model is not gonna work out, okay? So this brings me to tell you that the brain, the algorithms that runs us, cannot work without the body. So a body needs specific movements that need specific algorithms. And this is embodiment. This is the start of embodiment, okay? Most of the people now use embodiment as a buzzword to publish paper, but it means something, actually. Embodiment means that you cannot disentangle the body from the brain, okay? So when you see Google putting the same algorithm in different robots and they call it embodied, it's just no, okay? Don't. It's not. So this is how it works. It's not true. Now I do it again. Oh my God, what do I do? Fine. This is how it works, okay? So you see that it's putting in the center of the visual field what it's moving. The only thing that it's moving, okay? Now, here, there is not a single line of learning. All of the... I saw your face like, how the fuck? Yeah. It's because if you really follow nature, nature solves things nicely for you, okay? So you can add learning later on more complex things where learning is actually needed. To do something like this, learning, it doesn't make any sense because I got possibly 10% less in accuracy than a deep neural network trained on 3 big data sets, okay? Why should I? You know? Okay, now, fine. This is how it's working even with me at different distances, whatever, just to show, yeah, it's working everywhere, fine. Let's go on. So this became, I'm sorry, this also doesn't come out nicely, whatever. This became another project, of course, with, this Santa Claus is actually, yeah, this is actually, do you remember at the start when I was telling you, the first visual attention model famous from Loreniti, Christoph Koch, and Ernest Niebuhr from 1998. This is Ernest Niebuhr, and he's my best friend, honestly. We just had a meeting today, so we are actually trying now to write a big perspective paper. He's a professor at the Johns Hopkins University. He's not even, I mean, he's not just a Santa Claus, and is a professor in neuroscience, and we together, we try to understand how vision works, and we're trying to write a perspective together. This is another job, another work that came out with the Politecnico of Torino and the University of Sussex. So we are using the same model, and we are basically, this is Riccardo Pignari, which is a PhD student that I'm co-supervising, and he came here as a visiting. And with him, what we are doing is basically doing, the amacrine cells plus the motion direction detection. Do you remember those 4 milliseconds unbeatable motion detection direction? We are putting it on top of the amacrine cells. So not only we distinguish what it's moving in the scene, we also tell you what's the direction of motion, okay? All of it in possibly 5 milliseconds, okay? Let's see if I can get to the end of it. Now, this is the same model of before with the attention, with the OMS map and the attention map here. What you don't, this is me, it's not super clear, but this is me again, surviving my day. Let me show you, yes. Now, the difference here is that it's entirely running on spec, okay? So it's entirely running here. So in the previous paper that I published, I just get the events and I run things on my Mac. In this one, we are running on this neuromorphic platform here. So at the end of the day, this works with 1 milliseconds and less than 1 watt. Okay? In the other case, we have, of course, the watts of the M1, M2, whatever it is. Anyway, so this is a collaboration with, other best buddies. Okay? And we are running lots of things here. Okay, now, on this project that I worked, there is someone else, another of my angels, please come down, which is Ola. And Ola is a bachelor student, and she decided to do the project with me and the bachelor thesis, and I hope she will never leave me. And she... There's lots of people now they know, and she's working on this project.
Okay, so the goal of my project is neuromorphic object recognition through stabilization. At the start, we have the events accumulated from the event-based camera, and we go to the same proto-object detection, the attention, which Julia already told you about. And when we have the salient point, we can choose the region of interest. But the problem is that the object can be outside of the region, so we don't see it clearly. Yeah. So we perform fixational eye movements in order to increase the confidence of recognition the object. So in the end, we have the adaptive region of interest and the recognition, which runs on neuromorphic platforms on the Spinnaker. And when we are confident in our results, we can just move on to the next batch of the events and next recognition.
Thank you, Ola. Okay. So what is actually cool is that also the recognition part is running on Spinnaker, which is not super easy, okay? But she made it run. Okay. This is another angel that is not here, is Lukasz. And Lukasz is a master's thesis student, and he's doing the thesis with me. And we are working on spiking neural networks for drowsiness and sleepiness detection. Now became also blink detection. We are doing everything we can. So you can see that here you have the eye that is moving, and then we are trying to understand where the eye is, the pupil is moving, right? So we have the target and the predicted here in red, okay? Why with event-based cameras? Because of course you can catch very fast blink movements. It's easier, right? Because you can catch very fast movements. It's working kind of fine, okay? So this is the X position, this is the Y position, so you can see that you have the target in blue and the predicted in orange. It's working well, okay? Not crazy well, but it's working, okay? Now, fine. On top of this, we have also Rai. Rai just joined us, and she's a bachelor student, but from Brazil, from the Universidade Federal de Paraíba, which I feel I have already, lots of bananas. I'm so tired. So this is Rayan, and Rayan just won the RoboPollox challenge. So she will come here with this fellowship, her own fellowship, and she will be paid with this fellowship to then do the bachelor thesis here with me. And she's working with on keyword spotting. So what we are doing here is basically we have the attention, and what we want to say is, we want to communicate to iCub, look left. Look left, okay? All of, and this is like, oh, sure, whatever. But all of this in neuromorphic platform, okay? So this means keyword spotting on a neuromorphic platform. So this possibly means having a mini device that runs, again, turned on for 3 months with no charge or no battery required, okay? So there we go. Now, Okay, so this is of course a bigger problem, right? So it's a bigger problem. Like, I'm just talking about vision, but embodiment, so trying to talk about every single detail that matter, it becomes a problem of the entire body, right? So it becomes a problem of the soft actuators, vision, sensorite skins, proprioception, and so on and so forth, okay? And this is a paper that should come very soon, which I'm very happy about because it's Nature Machine Intelligence. Sorry, it took me 2 years. And this is, again, trying to push the co-design of the brain and body, okay? So trying to really push embodiment to the extreme that you need neuromorphic platforms. Why you need neuromorphic platforms? Because those little units, those little neurons can compute at different time scales. So if I have a hand that is moving over this table, I can compute all of the different things in a different timestamps, right? I couldn't with a CPU or with a GPU because I need to wait for all of them to a clock for all of the possible sensation that I feel, okay? This is just to tell you that an agent can indeed be part of a neuromorphic end-to-end pipeline. And this is a nice project that I've done in collaboration with the ETH Zurich, with Giacomo Indiveri and Lioba. Lioba is an incredible engineer, is her. An incredible engineer. I worked with her for 1.5 years, and then we published on scientific reports. And this is an entire pipeline where the robot is entire end-to-end neuromorphic pipeline, and the robot is following a painter. So you have an artist that is painting, and then the robot is following what the artist is doing on a canvas. So this means trying to understand the trajectory, trying to push not that much, because then you break the canvas, so all of it, okay? And this is end-to-end on neuromorphic platform. We didn't talk about analog neuromorphic platform, but this is also on analog neuromorphic, like a bloodbath, okay? Just to forget about it, okay? Nice. With this, we close this thing. Now, on the top left, together with Santa Claus, you see other people, which basically are the people I collaborated most. This is Michael Furlon, Milan from Sinsens, Giacomo Indiveri, Mattei here. Then here, this is my first podcast that I co-founded. It's called Brains and Machines. If you want to check it out, there's lots of nice people there. Rodney Brooks and all of the people that made Neuromorphic, so Toby Delbrook, like this, whatever. You don't know them, so it doesn't make sense that I tell them. But check it out. This is another podcast that I co-founded. Like, I kind of feel I had not enough things to do in my life. And this is Sotto Soglia. Sotto Soglia means sub-threshold in Italian. And it's because neuromorphic works in Sotto Soglia in sub-threshold for transistors. It doesn't matter, no. But what it matters is that I'm doing it with my lovely Fabrizio Ottati, and here we talk about how we like academia. So it's really, it's fun, okay? So if you want to check it out, it's on YouTube. Then I am the chair of all of these things, Open Neuromorphic, Neuropack, and Telluride. And if you want to work with me, I would be super happy. If you want to be part of my angels, you just drop me a message on LinkedIn or whatever you can find me. And thank you.
Okay, thank you, Julia. Now we have like 15 minutes for discussion.
Really? Okay. No.
Okay.
They're dead. How can it be possible? Shuban! Dai. Shuban here.
No, if someone else wants to go first, sure.
Oh, it's okay. We will do it in any case.
Okay.
We need to...
Yeah. So, my question is like something that you don't work on. But it was mentioned a lot of times during the talk, right? Which is RGB. And like currently RGB is not something that event-driven cameras can detect or even like work with. But eventually, if you want robots in homes to robots to be in homes and for them to use event-driven technology, they will need
colors.
They will need colors. Yes, exactly. So is there some work going on how to integrate RGB with?
You don't need RGB for that. You just need the contrast, right? In one case, you get the contrast in light. In another case, you get the contrast in colors. So there are even-based colored cameras.
Okay.
Yeah, you don't need RGB in any case.
Okay.
Yeah.
Yeah. Thank you.
There was someone else? Oh. Yeah.
I'm sorry, but 1 millisecond. How you can say 1 millisecond?
Because I tested it.
But without tolerances.
Without?
Tolerances.
What does it mean?
Okay, without tolerances.
What does it mean?
Tolerance. No, you have for sure some differences when you have different connections, different cables, different anything where you go through a system. You have always something which is making some resistances and so on. So how you can say like
so
once you said 4 milliseconds, when you said 1 milliseconds, and there was like not really something about what is the first and what is the end station. So you have 1 millisecond, but you have to go through a system. So 1 millisecond, what does it mean? For me, it was like something what is not able to catch.
Okay, so the cameras, I tell you 1 milliseconds, but the cameras goes nanoseconds. Okay, so the information that comes out from the cameras is in nanoseconds. Now, if you pass that information through a neuromorphic platform, the time to take 1 milliseconds of events and compute them in your neurons is 1 millisecond. So the computation takes 1 millisecond. Then if out of it, you need to then communicate, I don't know, for example, one of my problems is the pan and tilt, that it's very slow. So I go super fast, but then the pan and tilt needs the time to move. So that is actually where I lose all of my latency. For example, in my model where you have the pan and tilt that is going, I can show it to you, like it's a nice demo in these days. And basically I get out of everything, like it takes 10 milliseconds to acquire the data, process the data, get a point, and then to move with the pan and tilt, it takes me all of the other 110 milliseconds. So there I lose time. But the processing, the computation is very fast. So it's the computation that is 1 millisecond. Yeah, and that's why it's powerful. Yeah, but it's a bloodbath. Yeah. No, it's true. Yeah. It's true. Yeah. Do you have any other questions? Yeah? Yeah, possibly we can hear you. I don't know.
Okay, Julia, thank you for the talk. I'm interested in the further progress because you work in the, let's say, area of vision and visual attention, and you apply like a very new approaches to it. And there is no perfect like a time or not the time resolution. Time resolution is perfect, but you don't have this clock tick in your approach. So if you will go further and you will start to integrate with the, let's say, with the audio, with the language, with the proprioception, with the tactile, and all these sensors or this information will be based on your approach. And then you will start to do the multimodal integration. I mean, to have a task when you do have a language instruction and a vision. So do you have any idea whether your approach in the area of visual attention is somehow transferable also to other modalities, and whether you can then integrate them, having not the issues with something like you do have a binding problem even when what and where is like binding together. Yeah. So are you aware of this? Do you think about it? Do you have idea how to progress?
Unfortunately, yes. So it's a beautiful question. Now, the eventful works very well for the early stages. At some point, in very high level of the cortex, you have some spatiotemporal integration, which could resemble like a frame, but it's not. It's just, you know, a volume of space and time that you actually computed, and you have a response for that volume of space and time. So when you fuse the information together, I think you are in that level. Indeed, you are in the somatosensory cortex, which is very, very high. Okay. So what I'm doing at the moment is V1, maximum V2. Then in the V4, things get different, right? Because you have an information that it's processed again in a volume of space and time. So you can actually have some, I don't want to say synchronized, because there's nothing in the brain that it's synchronized, but kinda. You have some information that belongs to a bigger time period. So you integrate in space and time again, touch, audio, and so on and so forth. It's a matter of getting all of this spatiotemporal integration. Yeah. It's less eventful in higher cortex areas. So this is how I envision it, to do it. At some point I have an information that is a bottle. So I have this information that this is a bottle, and if I heard like this is a bottle for the last 1 minute, and if I heard, I don't know, a sound in the last 1 minute, possibly is the bottle if there is nothing else. You're not convinced? Kinda. Yeah, tell me why.
Yeah, but I mean, this is new. I mean, nobody's working in a multimodal integration for a spiking neural
No,
nets.
we do.
Yeah? Okay.
Yeah, we do.
Fine. So I think the synchronization will be difficult because you don't have, you know, something.
But it's not a synchronization. It's just, imagine you have two threads, and one is computing one information that you need, and the other one needs it. So when you get just the last information that come out from the other thread, the last, you know, useful information.
Okay, I can imagine in a simple task and in this basic visualization, but yeah. I mean, when there will be like a more, when there will be learning applied, I mean, the learning based on, you need to fuse this information, and then you have to somehow use it during the task execution. I think it will be difficult, but this is just my
But
guess.
because you possibly think about learning through backpropagation, which I don't think it's what we should do.
I mean any type. You don't need to.
No, because if you have local learning, then it works out. If you have very specific local learning, then it's working.
Okay. Yeah. I do have some doubts about the scalability
of local learning. Sure. And I have some doubts about backpropagation with the data that it needs. Yeah.
Okay.
Yeah, thank you. Yeah. Do you have any other questions? You still awake? Yeah. Shizon.
So I know that at some point you wanted to compare somehow, or at least think about a way to compare what you find with research on human, because you are inspired about what's happening with the vision, with the eye, with the brain, and everything. But have you done some work, or will you do some work on finding a way to compare what you do with what potentially humans are doing or animals are doing?
Is it?
Because the struggle that you have with trying to find, instead of using frames, you use events and everything. Yeah. It's also true in psychology, for example, where everything is representation. We're trying to find map in the brain, whatever. So we also struggle with that, and this is also probably not right. And so if somehow you can, because I feel like what you do could be nice to show another way, another direction for the research in psychology, for example. In your case.
This is a comparison with humans. These are 3D fixations from humans. Okay, so this is my saliency map, and this is the saliency map of humans. Okay, very difficult, because my model is a bottom-up model, so it's a very stupid model, and I'm comparing against a human being, so it's very difficult, but we have done it here, and it's also here. So I tend to do it as much as I can. Did we show it here? It's also here in the neuromorphic pipeline one, which is even better. Is even better because, again, these are 3D fixations. Okay, so these are fixations from real humans, and the data are slightly better because it's super localized and precise because it's neuromorphic, so it's very sparse. So we are better in a comparison with humans. So my problem is that actually I need to do everything. I need to compare with humans, but I also need to compare with classical ANN. Yeah. Yeah. But thank you. Yeah.
Thanks.
Thanks to you. Okay, guys. Do you have other questions? Are we still alive? Yeah? I want to just go to the end of it.
In your example that you were showing and the recognition between the cup and the apple, or I think it was, you showed the approach that the sequence of looking at the picture could classify the object itself. Have you done any testing, for example, in like the amount of entropy it takes to classify the object? I mean, I know this is not specifically what you do, but I see this as an interesting way to kind of classify objects or like do pattern recognition without actually processing the whole image. So I'm just like interested in if there were any like speed or power tests, and what was the approach in determining the next kind of segment to look at, because you start somewhere and then you have to move your eyes somewhere, or the
like this is 15 questions though, but
okay,
anyway.
sorry.
So the video that you saw, it's a video from a published paper that confirmed that you can do it. So you can classify through actions and sensory motor contingencies. So there is a proof that it's working, yes. There's lots of other people that are already working on it, and there is IBM that is working on it. There is me. Yeah, I'm trying to kind of convince other people to work on it. Now, the point is we need to understand how to make it work, because it's not easy, right? Like you cannot really rely only on the region of interest. It's better if you add the periphery of it, because then you have a global idea of what's going on there. Even though you don't get the information in super resolution, still you get a global sense of what's going on. Because otherwise, if you look here and you get only this, and then you look here and you get only this, it's very difficult to understand that these are the same object, unless the only thing that tells you that is that this comes afterwards this, and it's in time very close. But if you look at this here, and then you have also the periphery, then you cannot remember that there is some sort of information around it. So we are adding, because this is the work that Sharka is working on, we are adding also like the ROI and the peripheral information. Then you asked me also about the power consumption. No, we have no freaking idea, because at the moment it doesn't really matter. At the moment we are trying to understand if it works, if we can make it spiking. Once we make it spiking, then we can put it on neuromorphic platform. The idea is that I need, 1/16 of data than a classical ANN, right? I don't know if you want to add anything, or you're satisfied with my response. Yes. Okay. So that's it. It's kind of new still, even though we have proof. It's kind of new.
Yeah. So it's like a really complicated way to determine the next.
The next position, right?
Next position, yeah.
So the next position, at the moment, we are using the bottom-up attention, which is not enough. Because if the point is that when you have a kid and a kid has an object in the hand, right? The kid is moving the object in the hand. What is it doing? Is basically solving occlusion, right? Looking at different points of view. It doesn't even know it, but it does it instinctively, okay? But the point is, if I look here, I want to see here. So the movement of my hand depends on where I want to see. So there is a gazillion things that you need to think about. The proprioception, how to rotate the object, the vision. So everything is interconnected there. I don't know if you wanted to add, but it... exactly. Yeah. Okay. Yeah.
Okay, thank you guys. I will end it here.
Yeah.
And I would also like to invite you with us to this restaurant Pětník. I don't know. We have a reservation there.
Come.
8 if you want to come with us.
Come.
We're really happy. Yeah, and thank you one more time.
Thanks to you, and it was really nice. Thank you so much. Yeah.